Hi everyone, welcome to MOSFET. So this lecture is about diode connected load. Diode connected load is a very basic circuit which is used in analog design, but we need to know a lot about this circuit because it plays a very crucial role in some of the major blocks like current mirror circuit. If you talk about diode connected load is a very vital part of that circuit. We will be focusing on these three topics in this lecture. The first one would be about calculation of R out for diode connected MOSFET. So if you are looking from the drain terminal, how the R out value will be calculated. So we will derive it through small signal model. Second thing which we will discuss here is if diode connected load is excited by a voltage source, so how ID versus VDS or VGS curve will look like. And the third thing will be if we are exciting it through current source, then how the curve will look like. We will talk about these three basic points which are very important for diode connected load. So in this video, you will get to know about everything, every important thing related to diode connected load. So make sure you watch till the end. Many times when we use diode connected load, we see that it always operates in saturation region. So that's a very basic reason, but let's talk about that also. For saturation, if any MOSFET has to be in saturation, it needs to qualify this equation. VDS should be greater than or equal to VGS minus VTH. Now, since source is same here for drain and for gate also, so we can write it as VD minus VS equal to VG minus VS minus VTH, and this VS will get cancelled out. So ultimately VD should be greater than or equal to VG minus VT. Now, if you see, drain and gate are shorted. So if you have to make any MOSFET to work as a diode connected load, its gate and drain should be sorted. So as soon as you make it a shorted, this equation will always hold true, right? Because these two parameters are same. VD is equal to VZ. So if anything you are subtracting from one quantity, let's say if this is also same, this is also same. So this quantity will always be lesser compared to this. So that is why, since diode connected load always satisfied this equation, that's why we always say diode connected MOSFET always acts in saturation region, right? So this is one thing, but many times we use this diode connected load in circuits to replace an actual resistor, because resistor usually consumes a lot of area on chip. So instead of using a resistor, we can use a diode connected load which will have certain output resistance and it can act as a resistor. So what will be the R out if we are looking from drain terminal of this diode connected load? Let's calculate that so that things will get more clearer here. So if we have to calculate R out, we need to draw the small signal model for this MOSFET. So if we have to draw a small signal model, so we need to have one current source. Let's call this as GM into VGS. And along with this, there would be a parallel resistance of this MOSFET. Let's call this as RDS. We are calling this a source node and this is drain node. There would be a gate terminal and this is source terminal anyways. Now since it's a diode connected load, that means gate and drain would be shorted here. And if we have to calculate the output resistance of this diode connected load, we need to connect one external test voltage. Let's call this at Vx, and let's assume Ix current is being sourced by this voltage source, right? Now we need to calculate R out. So R out can easily be calculated if we calculate Vx divided by Ix. This will give us R out. So the first equation which we can apply here is that Ix would be equal to Vx divided by RDS plus, since we are applying KCL, so Ix some portion is going in this resistance and the other current is GM VGS. So the other term which will get added here is GM into VGS. We are not considering any body effect and all, otherwise one more parameter of body effect will come, but we are not considering that. Now VGS, if you see for this small signal model, so VGS would be equal to Vx here. So if we replace VGS with Vx, So Vx would come as a common and we will get 1 upon Rds plus Gm, right? Because this Vgs will get replaced by Vx. So Vx, if you take common, 1 upon Rds plus Gm will come. And as we mentioned, we need to calculate Vx upon Ix. So we will get 1 upon this parameter, 1 upon Rds plus Gm. RDS anyways for any MOSFET is quite high in terms, and if you are taking the 1 upon RDS value of that, so it will become very negligible. So ultimately you will get Vx upon Rx, that means R out equal to 1 upon Gm. And this is the value of R out looking from the drain terminal of diode connected load. So 1 upon Gm is the value. Usually you might have seen in any small signal model, if any diode connected load is getting formed, we directly replace its output resistance looking from drain by 1 upon Gm, but this is how we arrive at this value. So this was the small derivation, but it's important to know about this. Now let's address the second part of this question. Let's say you have a diode connected load and you are exciting this load through a voltage source. This is diode connected load and this is voltage V, and because of this voltage V some current I is flowing in the circuit, so we need to draw the curve of V and I. So because of V variation, how the current will look like for this diode connected load, that we need to draw here. Since we have studied just now, diode connected load always work in saturation region, that means we can write a saturation current equation which would be equal to ID equal to half mu n Cox W by L into VGS minus VT. Since VG is the same V potential which we are applying as source is 0, so VGS we can directly write as V. Let's call this as Vx. So we will be plotting between I and Vx, and this input will be Vx minus Vt or Vth threshold whole square. We are not considering again the channel length modulation, otherwise 1 plus lambda Vds term will come, but we are not considering that. Now if you see, till the point Vx will start rising from 0, there won't be any current flowing from this diode connected load, because because in order to have any current flow from this diode connected load, the value of Vx at least should be equal to Vt, so that current flow can start from this diode connected load. If you see from this equation, that also holds true. So from 0 to Vt level, there won't be any current from diode connected load. And once this Vx will start rising from Vt, the current will follow quadratic equation, so it will start increasing exponentially like this. So this is how the curve will look like between I and Vx for diode connected load. But there is a twist here. Let's say instead of using this voltage source, if we are applying a current source here, this is a current source, and let's call this current source as Ix. And because of this current source, let's say this voltage is being generated as V here. So we need to plot the curve I and Vx. So now on x-axis Ix will vary, and at y-axis we need to plot voltage, how the voltage will look like. Now you can't directly say it will be similar. There will be a twist here. Let's talk about that. So if you see here, we just now have applied this equation ID equal to half mu n Cx W by L and all. So from here, what we can do, if we have to calculate the value of this voltage, that means VGS, that is almost equal to V only because source is grounded. So if we apply this equation, what we will get? Vx or V value, we will get twice of ID upon mu n Cox W by L. This would be under root plus Vt. This is the value of Vx which we will get for diode connected load. Now the thing here is that if Ix is 0, there won't be any current flowing from this diode connected load. So ideally voltage should also be 0. But as soon as Ix will increase from 0 to small value, fraction of values, the same amount of current will start flowing from this MOSFET also. That means this MOSFET will be turned on in that condition. So as soon as Ix value will change from 0 to slightly above value, your voltage, this voltage will become equal to Vt, because this MOSFET has, if this MOSFET is turned on, then only the same amount of current can flow from this MOSFET. And if this MOSFET is turned on, that means its VGS is equal to Vt. And VGS here is denoted by V because source is grounded. So that means V is equal to Vt. So although we can say at 0 there won't be any current, but as soon as we are slightly increasing Ix, V value will become equal to Vt. So let's call this at Vt here. So this curve will start from Vt, but again there is a trick here. At Ix equal to 0, V will be 0. So, but we can't show it here because as soon as slight increase happens in Ix, V will become Vt. Now from here, if you see, as we will increase the Ix further, V will continue to increase, but this is under root of ID. V is equal to under root of ID and some Vt fraction is getting added on. So it will increase like this. It will not saturate, it will increase, continue to increase. So this is how the curve will look like between V and Ix. The only difference is that now this diode connected MOSFET is getting excited by a current source, and then we are plotting this V and I curve. In this curve, what we did, we excited this diode connected load with voltage source, and then we drawn the current and voltage waveform. So these two are important aspects of this diode connected load. That's what we usually do in current mirror circuits. In current mirror circuit, if you recall, the normal current mirror circuit looks like this. I reference we do, I reference we take, and we do something like this, right? So this is the reference branch. Here, reference current is taken here, and that is exciting this diode connected load, and this voltage is getting generated, which is being applied to the output branch. That's why this is important to know how the voltage and current curve will look like if we are exciting the diode with either voltage or current. So that's why it was very important topic. I hope something new you might have learned from this lecture. If you found this lecture useful, please share this with your friends. And if you haven't subscribed to our channel, please do subscribe. Thank you so much for watching.